So let's have a brief chat about these things we call real numbers. And as I mentioned when we were doing our factorising, it's the same idea as prime factors as what we do with real numbers. And so every natural number, and a natural number is of course, so the positive integers or the positive whole numbers, they are what we call the natural numbers, and they can always be written as the product of prime factors. So for example, 324, I know that's 4 81s, but we could keep going. 2 squared, 3 to the power of 4. Now, highest common factor. If you want to find it, then you write both numbers in terms of its prime factors. Then, basically, you're pulling out the common factors. That's what we did in algebra with factorising. So it's the same process. So let's use these two numbers. 1176, 252, 1176, 6 times 196, 3 times 2 times 49 times 4. So we have 3 times 2 cubed, 7 squared. 252, that's a little bit easier. 463s, 497, so we have 2 squared, 3 squared, 7. Now when you factorise, you always take out the lowest power in algebra. And this is why. Because when we find the highest common factor, it's the lowest power that they have in common, not the highest power. So our highest common factor, well, there's a 2 cubed and a 2 squared. 2 squared is the lower, so we pull that out. 3 to the power of 1 would be the lower, and 7 to the power of 1 would be the lower. And so 84 is the highest number, or the biggest number, that goes into both of those. Okay. So factorising removes the lowest power, and that is true for algebra as well. Lowest common multiple, well, that's what we saw with algebraic fractions when we're trying to create the denominator, and it comes from this. Again, we would write both numbers in terms of its prime factors, but this time we would write down all the factors without repeating. So I suppose when I did algebraic fractions, what I said is, if it's not there, put it down. So write down all the factors, basically. So 48 and 15, oh well, 2 small numbers. So 16 threes, 2 to the power of 4 times 3. 15 is simply 3 times 5, they're both prime. So write down all the factors without repeating. If it's not there, put it down. 2 to the power of 4, it's not there, I'll put it down. 3, it's not there, put it down. 3, oh, it's there, so I don't have to put it down again. And 5, it's not there, so I'll put it down. And in this case, if you had different powers, it would be the higher of the 2 powers that you would write down. So 240 for that particular number. I guess what this is illustrating is what we did in algebra and what we do with numbers is no different. Maths is math. The rules don't change because you're dealing with unknowns instead of knowns. All right, let's see how good we are. Divisibility, no cheating. I know it's written in front of you. No cheating. Divisibility tests. If you get in early, you'll get the easy ones. How do you know if a number is divisible by 2? Very good. It's an even number. Divisible by 3? Good. Sum of the digits divisible by 3. Divisible by 4? It's got to be the last 2 digits. Last 2 digits divisible by 4.
0 or 5.
You sure you're not reading? Very good. Ends in a 5 or a 0. Simply that. Divided by 2 and 3. Because 6 can be broken down into 2 prime factors of 2 and 3. So if it's divisible by both of those 2 prime factors, it must be divisible by 6. So it's an even number where the digits add to be a multiple of 3. Now I will be impressed if you can give me 7. Anyone actually know 7? This is a tricky one. Here we go. Okay? Double the last digit, subtract it from the other digits, then that answer, if it's divisible by 7, then the whole number is divisible by 7. Okay? Give me a number, hopefully not too small, or it's not that impressive.
21.
I could do 21, but again, not that that interesting? Give me a number divisible. We know it's divisible.
126.
Okay, 126. So we get the last digit, double it, subtract it from the other two. 12 minus 12 is 0. Is 0 divisible by 7? Yeah. So therefore 126 is divisible by 7. So there you go, that's 7. Double the last digit, subtract it from the other ones. If the answer is divisible by 7, the original number. All right, next one's a bit easier. 8. Right, now we go to the last 3 digits. So last 3 digits divisible by 8. 9.
They add up to 9. The digits of
Yes. So some of the digits is divisible by 9.
ends in 0.
Oh, very good. Ends in 0. Now we get to another interesting one. So what you do, imagine each digit has it alternates. Odd, even, odd, even, odd, even as you go along. So first position we'll call odd, second position we'll call even. If you add up all the even position digits, it should equal the sum of all the odd position digits or differ by a multiple of 11. Okay? So give me a big number. 120 is good, but it's not divisible by 11.
1,353.
1,353. So if we add the even position digits, we get 6. So I said that the wrong way around. They were the odd ones. But anyway, if we add the even ones, we also get 6. So they're the same. Divisible by 11. Divisible by 11. Fractions and decimals then. Let's have a look at those. Now, converting recurring decimals into fractions. That's probably the trickiest thing of it all, because everything else, when we talk about converting, is easy. Because to go from a fraction to a decimal is easy. Because a fraction, remember, is just division. And so you just perform that division and you get the decimal. Going from a decimal to a fraction, well, if it's a terminating decimal, again, easy because of the nature of our number system, because we're base 10. And so we know it'll be, 0.234 would simply be 234 over 1,000 because of place values. But what if it's not terminating? What if it's recurring? 0.6 repeater. I picked one that hopefully we know the answer to. Well, I can let x equal that. So in other words, x is 0.66666. I'm going to multiply both sides by 10. And so now 10x is 6.6666666 simultaneous equations. So basically, when I do this subtraction, whilst that repeating part goes on to infinity, I know they're the same, so they will just disappear. And I get 9x is 6, so x is 6 on 9, which is 2/3. Fantastic. Two numbers, 8, 1. And by the way, that's 8, 1, 8, 1, 8, 1, 8, 1, 8, 1, 8, 1, 8, 1, in case you're wondering. So I'll do the same idea. X is 0.81. So x is 0.81818181. Now it's no good this time multiplying by 10. Because remember, I want to cancel the 81818181. If I multiply by 10, I'm going to get 8.18181818. That's no good. Not the same. So this time I multiply by 100. And then the decimal part becomes the same. 8181818181. Can cancel. And we get 81 on 99, which simplifies down to be 9 on 11. All right. But what about if not all the numbers are repeating? In this case, only the 2 and the 7 are repeating. Remember the notation for recurring decimals. The first dot we put above the first number that's recurring, and the second dot goes on the last number that's recurring. So if you have more than 2 numbers recurring, you don't all of a sudden go and put a whole heap of dots there. It's just 1 dot at the start, 1 dot at the end. Now for this one, so that's 0.327272727. Let's try the same idea. X is 0.32727272727. Now, I want to cancel the repeating bit. when all the numbers are repeating, I have one number repeating, I multiply by 10. Two numbers repeating, multiply by 100. So the pattern seems obvious there. Three numbers repeating, multiply by 1,000. But what do I do if not all the numbers are repeating? Can I do exactly the same thing? Two numbers are repeating, multiply by 100. What do we get? I get 37.727272. So the number after the decimal point is not the same, but actually it's not a problem. Because once we get past that first decimal place, they are the same. So as I say, the 2727272727 will cancel. So we get 32.4 on 99, but that's unusual. We don't usually have decimals on top of the fraction. So multiply top and bottom by 10. There is 324 on 990, which simplifies down to be 18 on 55. But let's face it, that's a pain in the neck doing that. The reality is I don't do it that way. As I was saying last week, the beauty of mathematics is discovering patterns. And I'm going to do the same thing every single time there. When there's one decimal repeating, I'm going to multiply by 10. When there's two numbers, I'm going to multiply by 2. Every single time. So let's see if we can't work that pattern out. 0.6 repeater, you'll recall, turned out to be 6. And 6 was the number that was recurring. And it's over 9. So there's one number recurring. So I'm going to use 9. This is the pattern. What it means is, whoop, there you go, 2/3. 0.1 repeater will simply be 1/9. 0.2 repeater, 2/9. 0.3 repeater, 3/9. 0.4 repeater, 4/9. 0.5 repeater, 5/9. See the pattern? 0.6 repeater, 6/9. 0.7 repeater, 7/9. 0.8 repeater, 8/9. And here's the one that blows everyone away. 0.9 repeater, 9/9, which is of course 1. 0.81 repeater then, is there a similar pattern? And yes, there is. If I use the same idea, there's the fraction. I put 81 on top because 8 and 1 is what is repeating. And on the bottom, I'm going to put 99. Why 99? Well, there's two numbers repeating, so I'm going to put down 2 9s. And by 2 9s, I don't mean 18, I mean 2 9s physically. 9 on 11. So if there's two numbers repeating, I'm going to put it over 99. Three numbers repeating, I'm going to put it over 999, and so on and so on. So if I had this number, 0.7134 repeater, 4 numbers repeating, I could have done that algebra for sure, but it's quicker now to just go, oh, righto, there's the answer. 7134 over 9999. 7134, they're the numbers that are repeating. There are 4 numbers repeating, so I'll put down 4 9s, 9999. Okay, there we go, 2378 over 3333. Okay, but what about when not all the numbers are repeating? Here's the trick. I'm going to put 324 on top. How do I come up with that number? The number after the decimal points, if I just read it, says 327. But not all the numbers are repeating. The 3 was not repeating. So I'm going to subtract it. 327 minus 3 is 324. Okay. What will I put in the denominator? 990. Why? Well, I said when there was 2 numbers repeating, I'm going to put down 2 9s. But there's one number that's not. So instead of putting down a 9, I'm going to put down a 0. It makes logical sense to put that 0 at the end of the number. Because if I put it at the front of the number, it's not going to have any effect. 099 is 99. So we put it at the end of the number. So 2 numbers repeating, I put down 2 9s. 1 is not, so I put down a single 0. 80 on 55. So therefore, if I have something like this, 0.10, before you walked in today, you would have looked at that and gone, oh my gosh, how on earth would I turn that into a fraction? You might have gone to algebra to do it, but now you don't need to. Because on the top of the fraction, we'll go 1086. That's 1096 minus 10. because 1, 0 or 10 is not repeating. So we go 1,986, and on the bottom, 2 numbers are repeating, 2 are not. So I'm going to put down 2 9s and 2 zeros. 9900. There's our answer. That actually simplifies down. 181 on 1650.